Hi everyone, welcome to third lecture of Robotics and Controls. And today we are going to learn about coordinate frames and homogeneous transformation. So we'll discuss in detail the motivation of this chapter of this lecture, and also we'll derive how coordinate frames transformation can be written in terms of matrix multiplications and what are homogeneous transformations. But before that, let's just recall what we did in our previous lectures. So in our previous lecture did we learned about Python basics. We learned about several conditional statements like if else, loops, matrices, etc. We also had a lecture on Python plots and animation, which we'll use in our future lectures. So we learned using the plot function from the matplotlib library. Matplotlib library. We also saw how we can animate using the plot function. So we use the idea of a flip book. So for example, we plot one image, then we remove it with very instantaneously or very less time step, and then uh, display the other image instantly. It feels like in the it is animating. So this idea of flipbook we use for animation, and then we also showed the animation of a simple harmonic motion. So yeah, so let's now move ahead and first look at the motivation of uh, today's chapter or today's lecture. So I'll give you two examples to set up the motivation about why coordinate transformation and homogeneous transformations are useful. So let's say I have a wheeled robot. So this is the green shaded area is the main body, and the white shaded area are the wheels. Let it be initially at some position, uh, okay, and such that and let's have this red headlight, which tells us that it is pointing um, in the up direction. Now let's say it moves, and it moves, and then it changes its position and its orientation. Let's say um, so now let's say there is a sensor on the robot whose position on the base frame, or who how does it move, or its position is important to know. So for example, let's say we have a um, let's say we have some sensor, and let's represent it with this red dot, and we are interested in the position of this sensor with respect to the ground frame. Or let's say it is moving in a room, and these are the walls, and we are interested in the position of the sensor with respect to this corner. Then how do you do that? So that's the question. So the way to um, do that is you can obviously always apply um, geometrical principles, but what we are interested in is in a formula. So let's say we know how much the robot has moved or turned. We Based on that, we just need to know the position and orientation of the sensor. How do we do that? So the way we do that is we fix one uh, coordinate frame with the robot itself, and we know that this sensor's position with this respect to this coordinate frame, we always know that, and it's always fixed. And we represent the movement of this coordinate frame with respect to this base frame. So let's say we know how much theta it turned, how much distance xy moved, Based on these x, y, and theta, we can always know what the sensor's position is. In terms of how will we know it, we'll derive that. But that is why this coordinate transformation, study of coordinate transformation is so important in robotics. Another example that you can think of is that of a manipulator. Let's say I have a 3R manipulator which moves in a plane itself, and at the end there is an end effector. So let's say after some time it rotates, and uh, let me just show it with a dotted line. So let's say initially it was like this. Initially it was like this, and it moved and came to the new position. Now what is the change? Let's say we only have the information of the change in the angle of this arm. Okay, so but how do we know how much the end effector change with respect to the base point? So let's say I have it has picked an object, and I'm interested in its position and orientation. So you can always do it geometrically, but what we are interested is in a formula which would directly give the position, as if we know the values of theta 1, theta 2, etc. Sorry, this should be theta 3, 2, and the way it should be is theta 2 and theta 1. So let's say you know these changes, these change in angles. How do we say? So that is that we'll do in future. But all these problems, all these functions of the position of the object with respect to the fixed base frame, and will involve some coordinate transformation, and we'll try to understand them now. So in, as you see in all of these movement of the robot, uh, the movement involves always two types of movements, like translations and rotations. So let's first try to understand the coordinate transformation for pure translation. So let's say we look for pure translations. So in translation, let's say we have a fixed coordinate frame given by this white colored coordinate frame. Let's mark the origin as o naught, and x-axis as y naught, and y-axis as x naught, and y-axis as y naught. And let there be a robot. So I'll not draw the robot, but just assume that there is a robot, and there was a coordinate frame fixed with the robot, and the robot only translated from, it did not rotate, and it translated from o0 to o1. All right, now let there be a point c on the robot. Okay, let there be a point c on the robot. So we want the coordinate of this point c with respect to the fixed coordinate frame with origin o0. Okay, so let's see how to get it. All right, so I'll just mark the values of its x and y coordinates for us to for visualization purposes. So let's say this is x of c in first coordinate frame, this is y of c in first coordinate frame. All right, and this is x of c in zero coordinate frame, and this is y of c in zero coordinate frame. Right, and what is this This is the amount with which um, the coordinate frame has moved. So let's represent this with x naught and o naught. So let's say this is x naught and this is y naught. Okay, so using this, let's try to write the coordinates of C in different frames. So what is C naught? C naught is given by x C naught and y C naught, correct? Yeah. What is coordinate of C with respect to 1? This is given by xc1 yc1, correct? So let's say you know C1, you know this. So this and this superscript represent the frames. All right. Okay, let's say you know C1 and you want to find C0. Okay, this is you don't know, and you know C1. You also know by how much the coordinate frame has translated. That is, you also know O1 with respect to O0. So what is O1 with respect to naught? 0. It's x0 and y0. So as you can see geometrically, xc0 and yc0 are equal to x0 y0 plus x c1 and y c1. All right, which can be written as right. How is this correct? So you can see that xc1 is equal to x0 plus xc1, right? Similar in the case of y. So yc0 is equal to y0 plus yc1, correct? So this is how we got this relation. Now it can be written in simpler terms or in vectors in terms of c0 c1 and o1 naught is o1 naught plus c1. So this is the formula to remember, that the coordinate frame, the coordinates of the points on the robot with respect to the fixed frame is during pure translation is just the coordinate of the point C with respect to the moving coordinate frame plus the overall movement of the robot that by which the robot has translated. So this is fairly easy. One more thing, so you know what is O1 naught, right? What is O naught 1? Basically the coordinates of 0 with respect to the coordinate frame 1. It's easy to see that it's minus x naught and minus y naught. So if you change the order of the frames, the values take negative sign. So this is just a result that you should remember. But yeah, the more important result is this one, in which in pure translation, if you the way to get the coordinates of a fixed frame is addition of the coordinates with respect to the moving frame plus the amount with which the coordinate has the frame has moved. Okay. Now let's look at pure rotation. Okay, now let's look at pure rotation. Okay, so pure rotation means we do not have translation at all. So let's again draw the fixed frame. All right. Now let's draw the rotated frame. We'll name them in a short while. Just wait a second. Okay. All right. So let's just name them first. So x naught, y naught, o naught, and this is x1, o1, y1. Right. So let's say this rotated with angle theta. All right. And we have this C, point C. Okay. So the way it is, let's say we know the coordinates of C with respect to frame 1 as it was in the last case. So we know it from this. So let's say this is xc1 and this is yc1. All right. Just move it a little bit. All right. Now we want to know the coordinates of C with respect to the coordinate frame 0. Okay, so let's draw the perpendiculars. So this. All right. So you can see this is xc naught and this is yc naught. All right. So we want to calculate this. So how do we calculate? So let's just try to see what is xc naught. All right. So if this angle is theta, what is this angle? Let me use some other color. What is this angle? So because this is 90, this is 90, this is theta, this is 90 minus theta. So this is 90 minus theta, and which means this angle is theta. So this is theta. All right. So let me just erase this to get a clear picture. I'll draw it on the other side. This is y. Actually, this is this should be x. This should be yc1. Yeah, I was wrong. And this is xc1. Yeah. All right. Now, yeah. So how do we go about calculate xc naught? So so if you see xc naught, which is this value, right, is this length. Let me take some other color, pink. This length minus this length, correct? So let's write it down. So what is so this pink minus this white length, right? This is xc naught. So let's write what is the pink length. So it can be written as so we take the we use xc1's projection on this x naught line, so on this line, right? XC1's projection. So for that we need to know this angle. So it turns out that because this is 90 degree, right, and this is also 90 degree, because this is theta, this is 90 minus theta, right? Let me, so this is 90 degree, right, and this angle is also 90 degree, right? So if this is theta, this will be 90 minus theta, this angle, which means this is this is theta, right? So this angle is also theta only. Okay, with this geometry let's write the, so xc1 cos theta, so which is this pink line. White, what is white? How do we calculate the white one? So if you see, this angle is also theta, correct? Because again the same reason, this is 90 and this is 90, because this is theta, this will be 90 minus theta, and so this becomes theta. So yeah, so this is theta angle. Now if you see, this is yc1, all right, and the white arrowed line is same as this projection, right? This blue dotted line which I am currently drawing, this and this white arrowed line that we drew earlier is the same. So what we can write is, and this can be given as yc1 sine theta, right? So let's write yc1 sine theta, and we want to subtract from that. So this is how you get xc naught, right? In a similar fashion, I'll rub these pink lines and white lines just to make it clear. All right, in similar fashion you can also find the expression for yc naught. Okay, so yc naught is this value, yc naught is this value. Okay, so I'll not, you can do it, derive it and try to find it geometrically yourself. I'll just straight away write the expression for that, and it will be given by xc1 sine theta plus yc1 cos theta. All right, how does it come like this? So if you see, it is given by this projection plus it's given by this projection, which is a projection of yc1 and this is a projection of xc1 cos 90 minus theta, which gives sine theta, right? So yeah, you can do it yourself. It's not a very difficult task. Now let's move ahead and try to write this in matrix format, because that's how transformations are used. So matrix format. Okay, so xc naught yc naught equals cos theta minus sine theta cos theta into xc1 yc1. All right, I don't know where this come from. So yeah, so this is the expression of rotation. So there are and there is a matrix and there is a vector xc1, which is the coordinates of C with respect to frame 1, and if you multiply these two, you get the coordinates of C with respect to the base frame. So it's a very very clean expression, and we can write it in shorthand notation or in vector form. So this is called rotation matrix, because this matrix causes rotation of a vector 1 by some angle theta. So this is called a rotation matrix, and it is given by, so this it is represented by r1 with respect to 0. So rotation of 1 with respect to 0 into 1. So this is the expression which gives the relation between coordinates in frame 1, moving frame, with coordinates of fixed frame when it has rotated by some angle theta. All right. Now maybe sometimes it might happen that you know the coordinates in base frame, so you can just take an inverse and you'll get the same thing. So it turns out that this r10 is an r1 respect to O. This rotation matrix is an invertible matrix, so you can always find an inverse. Always find an inverse. So yeah, so let's try to, so if you try to find the inverse of this matrix, it will be something like this: cos theta sine theta minus sine theta cos theta. You can do it yourself. So so in the inverse of a 2 cross 2 matrix is fairly easy if you it's fairly easy, and you can calculate it, and it comes out to be this. All right, this is, we can write it as C1 equals this times C0. And you can see actually this inverse is just these two have been shifted, and this can be written as transpose of the rotation matrix. So actually these rotation matrices are orthogonal matrices, and for them R inverse is same as R transpose. So these are special matrices which are called orthogonal matrices, and for them R, this is always true, and R inverse is equal to R transpose. So the formula we were looking for, we can write that in red, is C0 equals R10 C1 and C1 equals R10 transpose C0. All right. Right. So these are the two formula for rotations. Okay. Now let's move on and look at combined rotations and translations. What happens if both rotations and translation happen simultaneously? All right. So let's draw the diagram first, and then we'll try to see how can we write that. How can we write the overall transformation expression. So let this be the fixed frame x0, y0, o0. Okay. Yeah, and let this be an intermediate frame, green frame, x1, y1, o1, which only represents the translation, and let this blue frame represent both translation and rotation. x2, o2, y2. So let it be rotated by theta. Okay, yeah. So, and let there be a point C, and it can be. All right. So yeah. So this is the thing. You can see that green has only translated with respect to the white frame. The blue frame has only rotated with respect to the green frame. But overall blue frame has both translated and rotated with respect to the white frame. Okay. So now let's just write the values for once. So I'll just 1 and O2, and first of all, how much has the origin of the translation has moved? X naught, Y naught. All right. Yeah. So this is what it is now, and it has been rotated by theta angle. Now we can also say that, let me use a dotted line. Okay, so let this represent xc 1 xc let's it represent xc1, and this represent yc1, right? And this is xc this is yc2, and this is xc2, right? Okay, so what has happened is the frame O0, x0, y0 has first purely translated to O1, x1, y1, and then it has purely rotated to O2, x2, y2. You can see O1 and O2 are coincident. All right. So yeah, so that's just trivial information. So it's pure translation here, and it's pure rotation here. So let's try to write the relation from which we had discussed in our previous lecture, previous sections. So yeah. So let's write for translation. So let's write for this first. Right, this relation first. Let's write it for this relation. Okay, so x c naught and y c naught can be written as the relation between x c1 and y c1. You just add the amount of translation it has done. So this is what you add. So this is the own pure translation relation. Now let's write the pure rotation relation. Okay, let's do that. So x c1 and y c1, and let me write it with the color it is. So x c1 y c1. Okay, so what I'll do is I'll bring the diagram on the side here, so that you can see Yeah, let me do that. All right. So, so basically xc1 and yc1, their relation with uh, xc2 and yc2 is what? Let's try to write that. So xc2 yc2, it is multiplied by rotation matrix. All right. So cos theta minus sine theta, cos theta. All right. So these are the two equations. Now let's put x1 y1 here. Okay. So what we'll get is x c naught y c naught is equals to x naught y naught plus cos theta minus sine theta cos theta matrix multiplied by x c2 y c2. All right. So actually you got the relationship between the final moved frame and the initial fixed frame coordinates. Okay. So this part here, this shows translation, right? And this part here, this is rotation. And together if you combine them, this is whole is translation and rotation. Now if you write it this formula in the small vector form, you can write it as C naught, which is C naught equals O1 naught plus R1 naught. So this matrix is R1 naught into C2. Oh, sorry, this is not R1 naught, this is R2 with respect to 1. Correct? So yeah, so this is the thing. Now so you can see the this only represents the name of the frames, right? So let's say there is no intermediate frame, then what? So let's say we directly want to write between two frames 1 and 2 like this, 0 and 1, let's say. So this is x1 y1 o1 and this is x naught o naught y naught. All right. So and this has rotated by theta and this is y naught and this is x naught, right? So then what will I, so because this only represents the name of the frames. Okay, so now because there is no intermediate frame, we can directly write C naught equals O1 naught plus R1 naught C1. Correct. So this is the formula that you should remember. It's an important formula that tries to that helps us tell when the relationship between the coordinates of a point in two frames, when one of the frame has both translated and rotated with respect to the other. Now this was one translation and one rotation. Let's say a frame goes multiple successive translations and rotations. How do we write the formula? Okay, so let's try to understand that. Okay, so 1.4, multiple successive translations and rotations. Okay, so let's say one transform occur from 0 to 1, so O1 X1 Y1. Okay, we can write the relation as C naught is equal to O1 naught plus R1 naught C1, right? Now let's say another translation occurred from O1 X1 Y1 to O2 X2 Y2. All right, I'm not drawing the diagram because we just want because we have a formula which represents all these transformations. These formula because of these formulas we don't even need to visualize them. All right, so yeah, so this can be written as C1 equals O21 plus R, rotation matrix of 2 with respect to 1, and coordinates of in frame 2. So let's say these are the two transformations. Now let's substitute 2 in 1. Let's try to find the overall transformation expression. So let's substitute 1 2 in 1 to get C naught equals O1 naught plus R1 naught plus O21 plus R2 with respect to 1 C2. All right, so let's simplify this. So C naught equals O1 naught plus R1 naught O21 plus R1 naught R21 C2. All right, so if you can see closely, we can divide this expression into two forms. One, this, which looks a lot like because it has the translation component of the frames, this looks a lot like translation, and this looks a lot like rotation part. So if we write it properly, we can say that C naught equals O1 naught plus R1 naught O21 plus R1 naught R21 C2. So this is rotation and this is translation. So what this expression is telling is that if you have a multiple successive transformations, you can always break them down in a single translation given by this expression O1 naught plus R1 naught O21 and a pure plus a rotation part where the rotation matrix R1 naught into R21. Okay, so yeah, so this expression tells us that. Now let's say these were only two transformations. Let's say we have n transformations. So let's try to this is for two transformations. Okay, to subsequent transformations. Let's say we have several transformations. Let's continue doing this. All right. So what will happen is, by continuing doing this, we mean O x naught y naught to O1 x1 y1 to O2 x2 y2, and so on and so forth till uh, On xn yn. All right. Now C naught equals. You can derive the expression yourself, but I am writing the expression here directly, and it will it will look like this. It will again can be written in two parts: translation and rotation part. So here I'm writing it. So O1 naught plus R1 naught O21 plus R1 naught R21 O32 plus so on and so forth, R1 naught R2 1 R3 2 and Rn minus 1 n minus 2 into O n n minus 1. All right, this is the translation part. Now comes the, let me change this color. C naught equals, this is the translation part, plus now comes the rotation part. What it will be? So yeah, so you can take a reference from this. So R1 naught R2 1 R3 2 so on and so forth, Rn n minus 1 into Cn. So this is the rotation part. So yeah, so for let's say you have n successive transformations, then this is the expression, which feels like a lot, right? So it's a very big expression. This quickly goes out of control. So and can we somehow make our life easier? So yeah, so this goes out of control very easily. So can we write this expression in a easier way, so that it's easier to remember, easier to like work around with it, and at this point, to solve this problem comes the homogeneous transformation. Okay, so at this point comes the homogeneous transformation. All right, so 1.5 homogeneous transformation. So what does it do is, so homogeneous transformation. So we saw that let's say we have a single transformation, C naught O1 naught plus R1 naught C1. All right. So let's say you have this representation. So a homogeneous transformation, what it does is, for a single transformation, instead of having these two separate parts, it gives a single expression of a single matrix multiplication. So you can write C naught prime equals H1 naught into C1 prime. So here prime means that we are dealing in homogeneous coordinates, and this matrix is called homogeneous transformation matrix. But how does this happen? Okay, so the homogeneous transformation matrix is given by H10 equals, yeah, so first one is R1 naught rotation matrix, The second part is O1 naught. Then here it's 0. So this is 0. This is not O. This is 0. And here it is 1. So these kind of, just to make it a square matrix, 0 and 1 are here to just make it a square matrix. So overall this is 3 cross 3 matrix. Let me use a different color. So we know that rotation matrix is 2 cross 2. O1 naught is a vector, 2 cross 1. 0 is here, 0 is given by 1 cross 2, so it's a vector. So this 0 vector is given by like this, 1 cross 2. All right. And this is 1 cross 1. So these 0 and 1s are just filler. How does it work? I will look at it. And now let's see how we represent this homogeneous coordinates. Okay, so the C naught prime will be given by C naught and an extra one. So we know that C naught is just 2 cross 1 vector, but we add just one extra one at the bottom to make it 3 cross 1. Okay, so this is just a representation in homogeneous coordinates. This is called homogeneous coordinates of C naught. Okay, and similarly we can write this for C1 prime can be given as C1 and 1. All right, we know that this is 2 cross 1 and this is 1 cross 1, and overall this will be 3 cross 1. Okay, so why this is helpful? Okay, and how does this relation hold? Okay, so let's try to see. So if we expand this, yeah, it will be something, let's say r1 naught is given by cos theta minus sin theta cos theta. All right, and C O1 naught is given by x naught y naught. All right, then how do we write this homogeneous coordinate? Then homogeneous matrix will be cos theta minus sin theta x naught, sin theta cos theta y naught, 0 0 1. This will be the homogeneous matrix. Okay, and what will be this homogeneous coordinate? So it will be, so let's say C naught is x C naught y C naught, and similarly C1 is x C1 y C1. Then this will be given by x C naught y C naught 1, and this will be given by x C naught 1 y C1 and 1. So this is just a representation. Now why does this expression hold true? Let's verify this expression once. Okay, all right, so what is h1 naught c1 prime? What it will be? So it will be cos theta minus sin theta x naught, sin theta cos theta y naught 1 0 0, and c1 prime will be x c1 y c1 1. All right, okay, so this will give us, so this is 3 cross 3 matrix, this is 3 cross 1 matrix, so it will give a 3 cross 1 overall 3 cross 1 vector. So what will the first row be? So x c1 cos theta minus y c1 sin theta plus x naught. So x naught multiplied by 1 will give us x naught. Right, similarly x c1 sin theta plus y c1 cos theta plus y naught. And at the bottom it will be 0 multiplied by this is 0, 0 multiplied by this is also 0, and 1 multiplied by 1 is 1. So at the bottom we'll get a 1. Okay. Now if you see this whole thing can be written as this part can be written as R10 C1, right? And this part can be written as O10, and at the bottom 1, which is same as C1 C naught prime, right? So actually that expression is true. The expression H10 into C1 prime equals C naught prime is true, right? So it actually it's just a simpler way of writing this whole expression, right? And why are we bothered to write it like this? Because this just makes it a matrix multiplication. So now if we want to do multiple transformations, we'll just multiply the matrices, and there will be no bigger extra terms, right? So what I am saying is, so we saw in a previous section that if we try to do multiple successive transformations and use the formula O10 plus R10 C1 equals to C naught, then it becomes a huge expression which quickly goes out of control. But here if we use this formula, what will happen is C naught transformation will just be a matrix multiplications of homogeneous matrices H n minus 1 C n prime. So it remains under control. All right. So this is the benefit of homogeneous transformation. Now we did it in 1 and 0 coordinates. Let's try to do it in general frames. So if we have general frame numbers, how we will do it? So I'll quickly do it and we'll then end the lecture. So we write H10, right? Instead of this, we'll write I minus 1 is given by R10, right? So it will be I minus 1 OI minus 1 0 matrix and 1. So we know that this is 2 cross 2, this is 2 cross 1, this is 1 cross 2, this is 1 cross 1, and overall this is 3 cross 3. Correct. Now let's try to write the homogeneous coordinate. So Ci prime is given by Ci and 1, right? And this is 2 cross 1, and overall this is 3 cross 1. So if you see Ci minus 1, the formula can be written as Ci minus 1 Hi minus 1 Ci prime. Right. So yeah, and if we expand it in general sense, we'll get the same thing. So Ci minus 1 equals Ri I minus 1 OI I minus 1 0 1 and Ci 1. You can also see if you because this is 2 cross 1 and this is also 2 cross 2 and this is the third column. You can actually use it as block matrices and multiply as block matrices. So this whole I can be multiplied by Ci plus OII minus 1 into 1, which is OII minus 1, and the bottom can be multiplied by 1. So this is Ci minus 1 and 1, which is the expression, which is the general expression of that we derived in our PGS section. So, and why this is used, we already saw, because this is a simpler representation, simpler way of writing. Okay, so that's all for today's lecture. We tried to discuss homogeneous, we tried to discuss coordinate transformation and also discuss homogeneous transformations. We saw translation, rotation, and both combined. We also saw how to deal with multiple rotations and translation, or multiple coordinate transformations. We saw that in the traditional sense, the way we use rotation matrices, it's complicated to write. So we then defined the homogeneous transformation and saw how it is easy to write the multiple successive transformation using homogeneous transformation. Now in the next lecture, we'll try to use these ideas to define forward kinematics and inverse kinematics of a manipulator. That is basically, if you know your joint angles, what is the position of your end effector, and if you know the end effector's position, what should be the joint angles. So these ideas will be useful there. So we'll use it there. Till then, you, and also if some of these topics you found to be difficult, you just you go through the lecture again and you try to do it by your own hand. So I think self study is the only way you can get hold of this topic if you find it a little bit difficult. For others, if this is basic, you'll find new things in the successive lectures. So yeah, so that's all for today. Thank you. We'll see you in the next lecture.